Good morning, all. In this lecture, I will explain the thermodynamics of ideal Fermi gas at low temperatures. In the last lecture, we started the discussion of thermodynamics of ideal Fermi gas, that is in lecture number 29. There we discussed three different cases, and the first one was when temperature T tends to infinity or the number density n tends to 0. In that case, the quantity n lambda cube by g, that is nothing but n h cube by g into 2 pi m kt raised to 3 by 2. This will be very much less than 1. When t tends to infinity and n tends to 0, this quantity will be very much less than 1. And we have seen that the specific heat capacity at constant volume was 3 by 2 nk. And the second case was when temperature T is very high, not infinitely high, and number density is low. Then n lambda cube by g is less than 1. Not very small, but it is simply less than 1. In that case, Cv was 3 by 2 nk into 1 minus 0.884 into n lambda cube by g plus etc. So, the meaning of this is when t tends to infinity, this lambda will go to 0 and you will get 3 by 2 nk, the same result. But for finite but very high temperatures, Cv will be less than this limiting value 3 by 2 nk because there is a negative sign. Okay, so that was case 2. Then we discussed the case when T tends to 0, that is temperature tends to 0. When temperature tends to 0, this n lambda cube by g will tend to infinity. And we have seen that the specific heat capacity Cv tends to 0. So, if you look at the plot of Cv versus temperature, we can see that this is something like this, a monotonically increasing function with temperature. And we already discussed these three regions. The region right to the this yellow line, that is T tends to infinity, then it saturates, Cv saturates to a value of 3 by 2 nk. This is actually Cv by nk, that is 1.5 means Cv is 1.5 nk, that is 3 by 2 nk for T tends to infinity. And this is the second case between this red and blue, that is high temperatures but not infinitely high. Then the value is less than 3 by 2 nk. So this is less than 3 by 2 nk. This dotted line represents the limiting value 3 by 2 nk. So this is less than 3 by 2 nk. And for T tends to 0, that is the region right at this black line, T tends to 0, then Cv tends to 0. Okay, so these three regions we explained already in the last lecture. Now I am going to explain the behavior at this region, that is around this green line. Okay, for very low temperatures but not tends to 0. Okay, low temperature region. Okay, and I have to show that this Cv is proportional to temperature, or Cv proportional to first power of temperature. Okay, that is our aim. In the low temperature region, the specific heat capacity of Fermi gas is proportional to first power of temperature. Right. So this case is case 4 and it is known as strongly degenerate. The case when T tends to 0, we call it as completely degenerate, and for low temperature case, we call it as strongly degenerate. Before going into the analytical study, we will carry out a physical assessment of the situation with the help of this equation. This is nothing but occupation number in an energy level with energy E is given by 1 by exponential E minus mu by kT plus 1. We already know that when T equal to 0, that is absolute 0 temperature, the chemical potential is called Fermi energy. Mu is known as Fermi energy. And the occupation number when T is equal to 0 can be either 1 or 0, depending on whether the energy is less than EF or greater than EF. When energy is less than EF, this numerator will be negative, and at a T equal to 0, this becomes e raised to minus infinity. E raised to minus infinity is 0, so you will get 1 by 1, 1. When E greater than EF, this value will be positive. EF is nothing but the value of mu at T equal to 0. So when E greater than EF, this numerator becomes positive, and as T equal to 0, this is e raised to plus infinity. E raised to plus infinity is infinity. So 1 by infinity is 0. So occupation number can be either 1 or 0. Up to EF, Fermi energy, occupation number is 1, and beyond EF, occupation number is 0. That is, the energy, all the energy levels up to EF are filled, and all the energy levels beyond EF are empty. Okay, now what happens to this curve when we increase the temperature slightly? Okay, so when T is finite but still less than Fermi temperature, okay, that is, you increase the temperature very slightly, then what happens to this graph? Okay, initially at T equal to 0, it was a step function. As temperature increases, what is the deviation of this graph? And the statement is, deviation from the graph at T equal to 0 when T is finite will be significant only for those values of E for which magnitude of E minus mu by kt is of the order of unity. What is the meaning of that statement? I will explain. This is a graph from Pathria's textbook, and here in this axis we have x, and that x is nothing but E by kt, and this theta is nothing but mu by kt, and these markings are theta plus 2, theta plus 4, etc. And the left hand side you have theta minus 2, theta minus 4, etc. Okay, so x is E by kt, theta is mu by kt, and occupation number we know that it is 1 by e raised to E minus mu by kt plus 1. We will consider 5 different cases. When x equal to theta, this E minus mu by kt becomes 0 because x and theta are the same. Then if you take the difference, then that will be 0. And occupation number will be e raised to 0. E minus mu by kt is 0. So e raised to 0 is 1. 1 plus 1 is 2. 1 by 2 is 0.5. So if you look at the graph for t greater than 0, at x equal to theta, the value is 0.5. At x equal to theta, the value is 0.5. Okay. Now, if you consider the point x equal to theta plus 2, that is E minus mu by kt is equal to 2. Then the occupation number will be 1 divided by E square plus 1. What is E square? 7.38 plus 1. This value will be 0.119. Okay. So at x equal to theta plus 2, the occupation number reduces to 0.119. At x equal to theta plus 4, it almost reduces to 0. What is exact value? At x equal to theta plus 4, you will get e raised to 4 at here. E raised to 4 is 54.59, and you will get occupation number as 0.017. So it almost reached 0. And if you consider the left side, x equal to theta minus 2, then epsilon E minus mu by kt is minus 2, and occupation number is 1 by 0.135 plus 1, and that is 0.881. For x equal to theta minus 4, that becomes 0.982. That is, it is very close to 1. That is, the deviation from the step function, the graph at t equal to 0, is only in a region around this Fermi energy, only in a very small region around this Fermi energy. And this difference is of the order of unity. Okay, only have to say when you reach up to theta plus 4, it is almost equal to the graph at t equal to 0. and when you reach at x equal to theta minus 4, you almost reach at the graph at t equal to 0. So the deviation is significant only in this range. Deviation is significant only in this range, and all the electrons or all the fermions in this range gets unaffected. So we can conclude that the thermal excitation of the particles occurs only in a narrow energy range, which is located around the energy value E equal to EF and has width of the order kT. When you give a temperature T to a system, the corresponding energy is kT. So the particles near to this Fermi energy and in a width of the order kT can get excited to the higher states. The bulk of the system remaining uninfluenced by the rise of temperature. Okay, due to the rise of temperature, only particles in this width can get excited. What is the number of particles that get excited at temperature T? We can say that it is the fraction of thermally excited particles is of the order of kT by EF, because all the levels up to EF are filled with one particle each. So the number of particles up to an energy EF will be definitely proportional to EF. And the thermally excited particle, that is only from this width. So the number of thermally excited particle will be proportional to kT. Total number of particles is proportional to EF. Number of thermally excited particle is proportional to kT. So the fraction of thermally excited particle will be of the order kT by EF. kT by EF. Okay. Now the totality of energy levels filled at T equal to 0, that is this red lines, the totality of energy levels filled at T equal to 0, that is known as Fermi C. Fermi C. Then the small fraction that excited near the top for T greater than C, we can compare it as mist above the sea. Okay, mist above the sea. The mist will be always in a region very close to the surface of the sea. Okay. Now, the origin of this behavior also due to Pauli exclusion principle, according to which a fermion of energy E cannot absorb a quantum of thermal excitation ET if the energy level E plus ET is already filled. What is the meaning? Suppose you have a particle at this point, say this is 10, this is 0, okay, at this point 10. So, and if it absorbs a quantum of energy 2, it has to go to this state. But that state is already occupied by one fermion. So it is not possible to sit the second. Pauli exclusion principle doesn't allow that. So a particle of energy E cannot absorb a quantum of thermal excitation ET if the energy level E plus ET is already filled. But at the same time, if a particle at this height, say 20, if it absorbs a quantum of energy 2, then it will reach at this green level, that is already empty. So no issue for this particle to go to this state. So it can get thermally excited. But for this particle, it is not possible to get excited by absorbing this much energy. So if temperature is very small, only particles from this width can get excited. So this is also a consequence of Pauli exclusion principle. This is also a consequence of Pauli exclusion principle. Okay. So only those fermions which occupy energy levels near the top level EF up to a width of order kT can be thermally excited. Okay. Why we made all these arguments? Because we can get a hint of specific heat of Fermi gas at low temperatures from these arguments. How? I will explain. The thermal energy per excited molecule is of the order of kT. At a temperature T, the thermal energy is of the order of kT. And the total number of particles that get excited will be n into order of kT by EF. What is this order of kT by EF? That is the fraction of particles excited to the higher levels. Okay, we already give an explanation for this. The fraction of thermally excited particles is of the order of kT by EF. So if you multiply it with the total number, you will get number of particles that excited. So total thermal energy of the system will be this number into thermal energy per excited particle. So if you multiply these two, you will get total thermal energy of the system. And that is of the order of n k square T square by EF. Now specific heat CV is dou U by dou T, that is the derivative with respect to temperature of this thermal energy. And if you take the derivative, you can see that it is T square, derivative will be 2T. So this quantity will be something like Nk into, there is K square, so I will write it as Nk into KT by EF. The classical value of specific heat is 3 by 2 Nk, and instead of 3 by 2 you have here KT by EF. And you know that KT by EF is very small, because KT, the width, is small compared to Fermi energy. So KT by EF is a very small value. So at low temperature, CV differs from classical value 3 by 2 Nk by a factor which not only reduces it considerably, but also make it temperature dependent. So here this factor introduces a temperature dependent also. Temperature dependence is nothing but T raised to 1. So CV is proportional to the first power of temperature. So that dependence we can make it from here, from these arguments. Okay, now I am going to derive this expression, that is CV, the dependence of temperature on specific heat capacity. Okay, for that, now we are considering the low temperature case, that is Z value is greater than 1. Z is fugacity, e raised to mu by kT. So for low temperatures, this value will be very much greater than 1. And we already know Fermi Dirac functions f nu of Z, that is given by 1 by gamma of nu, integral 0 to infinity, x raised to nu minus 1, z raised to minus 1, e raised to x plus 1. Z is e raised to mu by kt. Substitute here, you will get f nu equal to 1 by gamma of nu, integral 0 to infinity, x raised to nu minus 1, e raised to minus mu by kt plus x plus 1. For this variable, put u. U is equal to x minus mu by kt. Then du becomes dx, and as x tends to 0, u tends to minus mu by kt. As x tends to infinity, u tends to infinity. Therefore, f nu can be written as 1 by gamma of nu, integral minus mu by kt to infinity, mu by kt plus u whole raised to nu minus 1 divided by e raised to u plus 1 du. Now I will split this limit minus mu by kt to 0 and 0 to infinity. So I will get two terms. Then in the first term, put u equal to minus u. U equal to minus u. Then this becomes mu by kt minus u raised to nu minus 1, e raised to minus u plus 1. This du becomes minus du. And the limit becomes minus mu by kt, that becomes mu by kt. So mu by kt to 0. And if you incorporate this negative sign to the limit, you will get 0 to mu by kt. 0 to mu by kt. So that is why this first term becomes 1 by gamma of nu, integral 0 to mu by kt minus u raised to nu minus 1 divided by e raised to minus u plus 1 du. Second time, you keep it as such. Okay. Then 1 divided by e raised to minus u plus 1, you can write it as e raised to u divided by 1 plus e raised to u. and that is 1 minus 1 by 1 plus e raised to u. So substitute for this 1 by e raised to minus u plus 1, this value. Then you will get 1 by gamma of nu, this quantity is there already, 1 minus 1 by 1 plus e raised to u du, and the last term. You can multiply this factor to 1, you will get this term. You can multiply this factor to minus 1 by 1 plus e raised to u, you will get this term, and the last term is already here. So you will get 3 terms. Okay. In the first integral, and in this, put mu by kt minus u equal to x. So du will be minus dx, and as u equal to 0, x becomes mu by kt, and as u equal to mu by kt, x becomes 0. So this first term becomes 1 by gamma u. Actually the limits will be mu by kt to 0, but here instead of du we have a minus dx. So that minus sign can be used to interchange these limits. So that will be again 0 to mu by kt. Okay. So when you substitute for u equal to 0, you will get x as mu by kt. So this limit 0 to mu by kt will be actually mu by kt to 0. But this will be minus dx. You can incorporate that minus to interchange these limits. Okay. So final expression is 1 by gamma of nu integral 0 to mu by kt x raised to nu minus 1 dx. X raised to nu minus 1 dx integral is x raised to nu by nu. And you put the limit, you will get mu by kt raised to nu by nu. Okay. So instead of first term, you can write that plus second term and third term 1 by gamma of nu 1 divided by e raised to u plus 1. It is common. You can take that outside. And in the last term you have mu by kt plus u raised to nu minus 1. And the second last term you have minus mu by kt minus u raised to nu minus 1. That is written here. Okay, the first term plus. Now take a mu by kt outside. Then it becomes mu by kt raised to nu minus 1. From this term and this term, you can take a mu by kt outside. Then that becomes mu by kt raised to nu minus 1 divided by gamma of nu integral 0 to infinity 1 by e raised to u plus 1. If you take a mu by kt outside, this becomes 1 and this becomes ktu by mu. Here also this becomes 1 and this becomes ktu by mu. Now you can apply binomial expansion here, and this becomes 1 plus nu minus 1 into ktu by mu plus nu minus 1 into nu minus 2 by 2 factorial ktu by mu whole square plus etc. Similarly, you can apply binomial expansion in this term also. That becomes 1 minus nu minus 1 into ktu by mu plus nu minus 1 into nu minus 2 by 2 factorial ktu by mu whole square minus etc. So in this binomial expansion, all terms will be positive. Here alternate terms will be negative. What is the consequence of that? This 1 will cancel with this 1. This nu minus 1 ktu by mu will add up with this minus and minus plus nu minus 1 ktu by mu. So that will give you 2 nu minus 1. And this term will cancel. This third term will cancel. One is positive, the other one is negative. Next term will get added up. That will give you 2 nu minus 1, nu minus 2, nu minus 3 by 3 factorial. Okay. But there is a difference. In the second term, this is actually kt by mu into u. Here I write it as kt square by mu square into u. Why? Because outside bracket we have mu by kt raised to nu minus 1. I made it here mu by kt raised to nu by multiplying by a mu by kt. So I have to divide with a mu by kt also. That will make it kt by mu the whole square. When you divide it with a mu by kt, if you take that to the numerator, that will be kt by mu. Okay, so here you have only one kt by mu. This here you have square. Okay, that is because here this is raised to nu minus 1. Here it is mu by kt raised to nu. Okay. Now f nu is equal to 1 by gamma of nu mu by kt raised to nu into 1 by nu. This is the first term. And the second term, you can write it as This integral, we will write it last. And the second time is 2 into nu minus 1 into 2 into nu minus 1 divided by gamma of nu. 2 into, I multiply and divide with a nu. So that becomes 2 into nu minus 1. And there will be a 1 by nu also. And there is already mu by kt raised to nu. And this time is here. There is a 1 by gamma nu, and there is kt by mu whole square into u. Okay, there is 1 by gamma of nu, kt by mu whole square into that this terms integral 0 to infinity this u divided by e raised to u plus 1 du. Okay, that is there, plus the higher order terms. The next order terms will be there. Okay, so plus etc. Now we know that f nu of z is equal to 1 by gamma of nu integral 0 to infinity x raised to nu minus 1 divided by z raised to minus 1 e raised to x plus 1. This is the definition of Fermi-Dirac function. If you put nu equal to 2 and z equal to 1, you will get 1 by gamma of 2. Gamma of 2 is actually 1. Integral 0 to infinity x divided by e raised to x plus 1 dx. And this is a standard integral, and its value is pi square by 12. Pi square by 12. So we can substitute for this integral as pi square by 12. And there is a 2 here. So that becomes pi square by 6 in this term. And from these two terms, you can take a 1 by gamma of nu, mu by kt raised to nu, 1 by nu outside. Then in the first term, you will have simply 1. In the second term, you have nu into nu minus 1 into kt by mu whole square into pi square by 6. Here it is pi square by 12, but there is a 2 here. That makes it pi square by 6 plus higher order terms. Now, what is mu by kt? We have fugacity z is equal to e raised to mu by kt. So mu by kt is simply log z. So this mu by kt, I can substitute it as log z. And this kt by mu, I can write it as 1 by log z. Or kt by mu whole square is simply log z raised to minus 2. Log z raised to minus 2. So f nu of z is 1 by gamma of nu log z raised to nu 1 by nu into 1 plus nu into nu minus 1. This can be written as log z raised to minus 2 into pi square by 6 plus etc. If you put nu equal to 5 by 2, 3 by 2, 1 by 2, you will get these three Fermi-Dirac functions. Okay, that is useful for us. So f 5 by 2 of z, instead of nu, you have to put 5 by 2. That makes it 1 by gamma of 5 by 2 log z raised to 5 by 2 into 2 by 5. Because here you have 1 by gamma of nu into log z raised to nu and 1 by nu. 1 by nu becomes 1 by 5 by 2, it is 2 by 5. Plus 1 plus nu into nu minus 1, 5 by 2 into 3 by 2, log z raised to minus 2 into pi square by 6 plus etc. What is gamma of 5 by 2? Using recurrence relation, you can write it as 3 by 2 gamma 3 by 2, and it is 3 by 2 into 1 by 2 gamma 1 by 2. Okay, that is 3 by 4 root pi. Substituting here that value and solving, you will get 8 by 15 root pi log z raised to 5 by 2 plus into 1 plus 5 by 8 pi square into log z raised to minus 2 plus etc. So this is an expansion of Fermi-Dirac functions in powers of log z. Similarly, f 3 by 2 z you can written as 4 by 3 root pi log z raised to 3 by 2 1 plus pi square by 8 log z raised to minus 2 plus etc. And f half of z is 2 by root pi log z raised to half into 1 minus pi square by 24 log z raised to minus 2 plus etc. Okay. Once we have these three functions, we can go to equation number 8 from the last lecture. That is n by v equal to g by lambda cube f3 by 2 of z. Put f3 by 2 of z this value, then you will get n by v equal to g by lambda cube is actually h cube divided by 2 pi m get raised to 3 by 2, that will go to numerator, into 4 by 3 root pi log z raised to 3 by 2 into 1 plus pi square by 8 into log z raised to minus 2 plus etc. Okay. It is 4 pi g by 3, 2m by s square raised to 3 by 2 And log z you can again substitute back as kt log z, not here you have a kt raised to 3 by 2, here you have log z raised to 3 by 2, so that becomes kt log z raised to 3 by 2 into 1 plus pi square by 8 into log z raised to minus 2 plus etc. Okay, this is n by v. Now in the zeroth approximation, you can neglect this term onwards. You keep the first term only. That is zeroth approximation. That is the approximation when t tends to 0. When t tends to 0, log z is equal to mu by kt, that will tends to infinity. So log z tends to infinity means log z raised to minus 2 will go to 0. So you can neglect this term onwards. That is zeroth order approximation. Then n by v becomes 4 pi g by 3 2m by s square raised to 3 by 2 kt log z raised to 3 by 2. From here you can find kt log z, and that is 3 will go to this side, 4 pi g will go to this side, that will make it 3n by 4 pi g v raised to 2 by 3, because here it is kt log z raised to 3 by 2. So when you find kt log z, you have to take a whole raised to 2 by 3. Then you will get 3n by 4 pi gv raised to 2 by 3, and this becomes h square by 2m. This is nothing but the expression for Fermi energy. Okay, kt log z is actually chemical potential, and we already seen that at t equal to 0, chemical potential is Fermi energy. So this is exactly the same result. In the zeroth order approximation, you will get the same result we obtained earlier. Okay, in the next approximation, we have to keep one more type, this term. Then n by v becomes 4 pi g by 3 2m by h square raised to 3 by 2 kt log z raised to 3 by 2 into 1 plus pi square by 8 log z raised to minus 2. Okay, kt log z is a chemical potential, and you can call it as Fermi energy. Okay, when t tends to 0. So log z you can write it as EF by kt. Okay, log z you can write it as Fermi energy by kt. So instead of this log z raised to minus 2, you will have kt by EF whole square, because log z is EF by kt. This is log z raised to minus 2. So this becomes kt by EF whole square. Okay, using this relation, we can find kt log z. You can invert this relation. Okay, you can take this whole quantities to this side and find kt log z. Then you will get kt log z equal to 3n by 4 pi gv whole raised to 2 by 3 h square by 2m into 1 plus pi square by 8 kt by ef whole square whole raised to minus 2 by 3. This is the value of kt log z in the next approximation. And the term outside bracket is actually ef. So it is ef into 1 minus pi square by 12 kt by ef whole square. So if you put t tends to 0, you will get again the Fermi energy. So this is the next approximation type. Okay, now we have an equation for internal energy, 3 by 2 nkt into f5 by 2z by f3 by 2z. We already have equations for f5 by 2z and f3 by 2z. Substitute that values here. 3 by 2 nkt into f5 by 2z is nothing but 8 by 15 root pi log z raised to 5 by 2 into 1 plus 5 pi square by 8 log z raised to minus 2 plus etc. f3 by 2z is 4 by 3 root pi log z raised to 3 by 2 1 plus pi square by 8 into log z raised to minus 2 plus etc. So internal energy U equal to 3 by 5 nkt log z. This log z raised to 5 by 2 and log z raised to 3 by 2 will cancel, and you will get a log z in the numerator. And this 8 and 4 will cancel, you get a 2 here, and that 2 will cancel with this 2. 15 and 3 will cancel, and you will get a 5. So that makes it 3 by 5. 3 by 5 nkt log z. This term is already here. This term whole raised to minus 1. Using binomial expansion, that becomes 1 minus, here it is plus. When you take whole raised to minus 1, you will get 1 minus pi square by 8 log z raised to minus 2 plus etc. Okay, 3 by 5 nkt log z, 1 into 1, you will get 1. Then 1 into minus pi square by 8 log z raised to minus 2 is there. Plus 5 pi square by 8 log z raised to minus 2 into 1 is here. So from these two terms, this is 5 by 8, this is minus 1 by 8. So you will get 4 by 8. So the second term will be 4 by 8 pi square log z raised to minus 2 plus higher order terms. So u by n is 3 by 5. What is kt log z? Kt log z, in the next approximation you have this value. So substitute this value for kt log z. So this quantity. Again 1 plus 4 pi square by 8 is simply pi square by 2 kt by ef. Log z you can write it as kt by ef whole square. Plus log, not log z. Log z is actually ef by kt. So log z raised to minus 2 is actually kt by ef whole square plus etc. Again this is 3 by 5 ef. 1 into 1, 1. Then 1 into pi square by 2 kt by ef square is there. And minus pi square by 12 kt by ef square into 1 is here. So from these two terms you have this is pi square by 2. When you take LCM, you will get here 6. 6 minus 1, it is 5. 5 by 12 pi square kt by ef whole square plus higher order terms. This is the equation for internal energy per particle. So CV, specific heat capacity, is dou U by dou T. So it is CV by Nk, that you can write it as 1 by Nk into dou by dou T of U. U is, you can take this N to this side. So 3 by 5 NEF is constant, then dou by dou T of this quantity. When you take derivative of this quantity with respect to temperature, this one derivative is 0. For this quantity, derivative is T square, it is 2T. So this 12 becomes 6. So it is 5 by 6 pi K by EF whole square into T. So solving this, cancelling the terms, 5 you can cancel, 3 and 6 you can cancel, and you will get pi square by 2 into kt by EF. So CV by Nk is pi square by 2 into kt by EF. CV proportional to the first power of temperature. Okay. And the pressure for an ideal Fermi gas, it is given by 2 by 3 of energy density. Energy density, we already have energy per particle, this equation. So you can take this n to this side. Then U by V, energy density is 3 by 5 into n by V. N by V is actually small n into EF into this term. So you can substitute that value here. So you will get 2 by 5 n EF into 1 plus 5 pi square by 12 kt by EF whole square plus etc. So this is the equation for pressure of ideal Fermi gas at low temperatures. This is the specific heat of ideal Fermi gas at low temperatures. It is proportional to T. Okay. Now expression for U by N and P are identical with the ground state result when T is equal to 0. Okay. See the equation for U by N when T equal to 0, that will be simply 3 by 5 EF. This is the same result we obtained in the case 3. 3 by 5 EF. And pressure, if you put T equal to 0, you will get 2 by 5 NEF. And exactly the same result we obtained in case 3. Okay. Also CV by Nk is pi square by 2 into K by EF into T, that is proportional to T. And in the limit T equal to 0, CV becomes 0. So this is the behavior of graph. So far we explained this region. Okay, so far in this lecture we explained this region, the low temperature region. CV is proportional to T. That is, this dotted line is CV equal to T. So CV linear behavior is shown in this dotted line. So for low temperatures, CV obeys linear behavior. Okay, then there is departure, and finally it saturates to a value 3 by 2 Nk. Okay, so this is the explanation of this graph at a low temperature. Now we can calculate Helmholtz free energy. It is given by A equal to mu n minus PV. So Helmholtz free energy per particle, A by n, is mu minus PV by n. What is mu? It is kt log z minus PV by n. Kt log z, in the second approximation you have EF into 1 minus pi square by 12 kt by EF whole square plus etc. minus PV by n. PV by n is minus 2 by 5 EF into 1 plus 5 pi square by 12 kt by EF whole square plus etc. Why? Because we already have an expression for P, okay, this quantity. This n is actually capital N by V. So you can take that V to this side and N to this side. So PV by N becomes 2 by 5 EF into 1 plus this quantity. That is exactly here. Okay, so A by N is equal to, here you have an EF and minus 2 by 5 EF. That makes it 3 by 5 EF. And this is minus pi square by 12, and this is actually this 5 and 5 will cancel. It is minus 2 by 12. Okay, minus 1 by 12, and this is minus 2 by 12. That makes it minus 3 by 12, and it is minus 1 by 4. That is exactly, if you multiply this quantity with this quantity, 5 and 5 will cancel, 3 and 12 will cancel to get minus 1 by 4. So the second time is here. So Helmholtz free energy per particle is 3 by 5 EF into 1 minus 5 by 12 pi square kT by EF whole square plus etc. What is entropy? Entropy per particle, you can write it as U minus A by NT. This 1 by T you can take outside. Then what is U by N? U by N we already have this expression, U by N. 3 by 5 EF into 1 plus this quantity. Substitute that. 3 by 5 EF into 1 plus that quantity. A by N, you have this. So minus 3 by 5 EF, 1 minus 5 by 12 pi square kT by EF whole square plus etc. So this is 1 by T into 3 by 5 EF minus 3 by 5 EF will cancel. Then the next 5 by 12, the second time will get added up. Okay, so that is 3 by 5 EF into this 5 by 12 and 5 by 12 added up to give 5 by 6 into pi square kT by EF whole square. This is entropy per particle. And the final expression is S by Nk equal to pi square by 2 into kT by EF plus etc. And you can see that in the case when T tends to 0, this entropy goes to 0. That is in accordance with the third law of thermodynamics. At absolute 0, entropy vanishes. Okay, so this is all about the thermodynamics of ideal Fermi gas at low temperatures. Okay, so this is the explanation of this region. Okay, in the last lecture we explained the other three regions. So we could explain the variation of specific opacity with the temperature using this theory. Okay, thank you.